So in this video, I will be deriving the torque balance for two concentric cylinders as seen in the Cuvette viscometer. So what this viscometer is it's basically a device for measuring the viscosity of a liquid. So what we have is an outer cylinder, and inside that outer cylinder is a smaller inner cylinder, and in between those two are the liquid that we're measuring the viscosity of. So you apply a torque on this rod right here, and it spins the inner cylinder. And so the equation that I'm going to be deriving will show that the torque on the inside of the cylinder is balanced with the torque on the outside of the cylinder. You can kind of think about stirring a cup with your finger. When you stir the cup, if you don't hold the cup down, the cup will kind of stir on the table along with it. And so to keep that from happening, we need to apply a torque in this direction to keep the outer cylinder from moving at all for this viscometer. So I also have two equations on the board. The first one is our velocity profile equation. I'll explain that in a second. And then we also have the equation for shear rate. So in the viscosity profile equation, there is K, which is just the ratio of the inner radius over the outer radius. And that'll come into play a little bit later for our equation. And so if you take a top-down look view of this viscometer, we have our two cylinders, there's fluid in between them, and we have our inner radius, which is R sub I, and our outer radius, which is big R. And so for this scenario, we are assuming a no-slip boundary condition, which basically means the velocity of the liquid against the surface is equal to the velocity of that surface. So, for example, the velocity of the liquid against the outside cylinder is going to be equal to the velocity of the outside cylinder, which in this case is 0. So the fluid against the outside cylinder has a velocity of 0. And then if you take a look at the inner cylinder, the velocity of the fluid against that is going to be equal to the velocity of the inner cylinder, which can be written as the inner radius times the angular frequency omega. So using this property, we are able to get the velocity profile, which basically explains the velocity in between these two cylinders at some radius r. So it's obviously going to be in between 0 and the velocity of the inner cylinder, and that value will be given by our velocity profile equation. And then it's going to be used in our shear rate, which we'll use to get the torques. And the shear rate is just the derivative with respect to r of our velocity profile equation over r times the radius. And so to first get at the torques, we need to look at the definition of a torque. And that is just the force perpendicular times the distance r in this case. And now I'm going to be kind of using this base equation and substituting lots of other relationships into it to make it a little bit messier, but you'll see later on that we'll use it to prove that the torque on the inner radius and outer radius are equal. So to get at the torque on the inner radius, which is what we'll start with, or on the inner cylinder, which is what we'll start with, we need to first express the force in terms that we know. So I'm going to be using shear stress, which is also a variable of tau. I'm just going to use it as S so we don't get it confused. So this is shear stress, and that equals force over area. You can also, if we're working with a Newtonian fluid, which in this case we're assuming a Newtonian fluid, shear stress can be represented by the viscosity of the liquid times the shear rate. And so we're first going to be using this definition and plugging that in for our force. So our new torque equation is going to be the shear stress times our area times the radius. And then we can again use this. Our shear stress is the viscosity times the shear rate. And we'll plug that into our torque equation. So it will be the viscosity times the shear rate times our area. The area of the cylinder is easy, so I'm going to kind of leave it towards the end. We're going to first try to get at the shear rate of the inner cylinder. So to do that, we need to take the derivative of this equation. So the shear rate of the inner cylinder will be equal to the radius of the inner cylinder times the derivative of this equation over r. So I'm just going to rewrite it and divide by r. So these terms will be unaffected, but this will become our outer radius squared over the inner radius squared minus 1. So just rewriting that equation down here. And then since we're dividing by r, it will be the outer radius squared over the inner radius squared minus 1. And so to take the derivative of this whole term here is just a constant. And so we're taking the derivative of this expression. Since the outer radius is constant, that can be pulled out. The inner radius, we will take the derivative of that, which will just be the derivative of r to the negative 2 power. And then the derivative of a constant is 0. So I'm going to go ahead and rewrite this. It will be negative 2 omega, because this is negative 2 times r to the negative 3. So I just pulled that negative 2 out front, times k squared over 1 minus k squared times r squared over r I squared. So just gonna erase this right here so you can see it a little clearer. And so if you see, we have the inner radius squared in the denominator and the radius squared, or just the inner radius over here. So this will cancel out with this. So the torque on the inner radius will be negative 2 omega times the ratio of our radii squared over 1 minus the ratio of the radii squared times our outer radius squared over the inner radius squared. And so if you haven't noticed already, this is just the ratio of the outer radius squared over the inner radius squared. So we can use our definition of k to rewrite this in terms of k. If you invert this, so k to the negative 1 will be our outer radius over the inner radius, and then we have to square it. So this whole expression here is equal to k to the negative 2. This k to the negative 2 power is going to cancel with this k squared, and we can rewrite this a little simpler. So the shear rate for the inner cylinder is going to be equal to negative 2 times omega times 1 over 1 minus k squared. And that cleans up nicely. So now we can plug this back into our torque equation to get the torque for the inner radius. So what that's going to look like is we're still going to have viscosity times area, which in this case, the area is just going to be 2 pi r times the height. And so the height will be defined as the height of these cylinders. I'll just call that h. So we have the viscosity times our area, which is 2 pi times the inner radius times h. And then we have our shear rate. So that is going to be negative 2 omega times 1 over 1 minus k squared. And so I'm going to clean this up and write this torque equation kind of in the corner so we can use it later to compare to the torque on the outer cylinder once we reach that. So the torque on the inner cylinder is going to be negative 4, because we have 2 times negative 2 pi. So we've got this omega times we need the radius up here. So instead of just being r, it'll be 2 ri. And so this will just end up being r squared. That was just a small mistake. I forgot to carry over the radius for our torque equation. So going from here, it'll be negative 4 pi angular velocity times the inner radius squared. That takes care of these, times the viscosity of the fluid, times times the height times 1 over 1 minus k squared. And now I'm going to erase some of this so we can derive the equation for the torque on the outer cylinder, which hopefully, if the torques are balanced, will be the same. So coming back to here, to get at the torque on the outer radius, we just need to take the derivative of this again, which ended up being -2 omega times k squared over 1 minus k times r squared over r cubed times r. And so these cancel out again, and so this just leaves us with r squared. And looking at this, since we're looking at the shear rate for the outer cylinder, this radius is just going to be the radius of our outer cylinder, which is big R, and so this whole term will cancel out. And I'm going to rewrite this equation. And plug it into our torque equation, the same way we got the torque for the inner cylinder. So the torque on the outer cylinder is going to be viscosity times the area, which is going to be 2 pi big R this time times h times big R times the shear rate for the outer cylinder, which is just -2 times the angular frequency times k squared over 1 minus k squared. And if you notice, this becomes r squared because we have an outer radius here and an outer radius here. So I'm going to erase that and rewrite it over in the numerator over here. Since these are all being multiplied out, we can. And then I'm actually going to use our definition for k again to rewrite this. So r squared, I'll just do it off to the side over here. R squared, and then k squared is just going to be our inner radius squared over the outer radius squared from here. And so these two will cancel out, and this will just become the inner radius squared. And now I'm just going to rewrite this. If you can see where we're going, once I rewrite it, it should be identical to this equation here. So the torque on the outer radius is going to be, again, -2 times 2 is -4 pi times omega times the inner radius squared times our viscosity times the height times we're left with 1 over 1 minus k. 1 minus k squared. And so as you can see, these equations are identical. So the torque for the inner radius and the torque for the outer radius are identical, which means that these torques balance out. So when we run our viscometer and apply a torque on this shaft to spin the inner cylinder, the torque on the outer cylinder will balance out so it does not move.